Okay, the random variables that we have been discussing so far were discrete random variables. So in that, the random variables can take a finite set of discrete values. Okay. Accordingly, the PDF, the probability density function of the random variables, is discrete. Okay. So here there we plot xi and probability of x is equal to xi. So x is the random variable, xi denotes the real values which the random variable can take, and px is equal to xi is the probability of the random variable x getting a value of xi. Okay, so we have seen certain PDFs, probability density functions. Okay, so in the discrete random variables, the values which the random variable can take, they are discrete, and you definitely have a finite set of values. Okay, but in the continuous random variable, the random variable x can take, in general, in any certain interval, it can take infinite possible values. Okay, it can take infinite number of values. So defining the probability of x is equal to xi in this case is certainly 0. Okay, because the number of values which the random variable can take is infinite, so the probability of getting a value, specific value of x equal to xi is technically 0. Okay, because it will be divided by infinity. Okay, that value divided by infinity, because we have infinite number of values which the random variable can take. So the probability of getting a particular value in a continuous random variable is generally 0. Okay, like suppose if I suppose the example of a continuous random variable, maybe you have a circle. Okay, and this is the center of the circle, and you throw a arrow on the circle, and wherever this arrow hits, maybe here or here, and if you measure the distance of this point from the center of the circle, and if you map that on the real axis, this random variable x will turn out to be a continuous random variable. Okay, because if I say suppose r is the radius of the circle, so the minimum value that the random variable can take is of course 0, and the maximum value is r. But between 0 and r, this arrow can hit on any point. Okay, and accordingly the distance of this point from the center of the circle is basically continuous. It is a continuous variable. Okay, so in such a case, I will say, if I define that the probability of getting x is equal to some point here r naught, that is definitely 0. Okay, likewise, if you say, if you measure the temperature of any location in a city, and if you assume that the temperature is continuous, that the temperature can take any random value, and in the range of suppose 5 degree to maybe 55 degree, then the probability of having a temperature equal to maybe 34 degree, definitely the probability of getting temperature is equal to 34 degree is 0. Okay, because we have assumed that the temperature can take any value between 5 degree and 55 degree. It means you have a continuous range of values, infinite number of points you have. The probability of getting a particular value in a continuous random variable does not make any sense. Okay, so that is why we basically, when you discuss the continuous random variables, we start with the CDF rather than PDF. Okay, which is called as cumulative distribution function. This is cumulative distribution function. So the cumulative distributive function, the CDF of a random variable x is denoted as f capital F x of x is the probability that the random variable x takes a value which is less or equal to x. Okay. So remember, when you write this italic x, this denotes the values of the random variable which can take. Okay. This is how we define the CDF of a random variable. So given a random variable x, the CDF of the random variable f(x) of x is basically the probability of the random variable having a value equal to or less than x. Okay, and it certainly has certain, you can say, properties like f(x) of x is greater or equal to 0, definitely, because the probability cannot be non-negative. f(x) of infinity is going to be 1, because when you take x as infinity, then the probability of the random variable x getting less or equal to infinity, it includes the entire sample space, and definitely it is going to be 1. Okay, f(x) of minus infinity is of course 0, because the probability of x less or equal to minus infinity will make it 0. Okay, and the third important property of this is that fourth important property, that f(x) of x, which is a CDF, it is a non-decreasing function, or you can say it is an increasing function. Okay, so non-decreasing function means that if I suppose have a plot of x versus f(x) of x, maybe it has any plot, not like this, it will be a non-decreasing function or increasing function. It means if you take any 2 points, x1 and x2, so the CDF of the random variable at x1, that is f(x) of x1, will be less than or equal to f(x) of x2 if x1 is less or equal to x2. Okay, and that should also be there, because if x2 is greater than x1, then the probability of the CDF of x2 is the CDF of the random variable at x is equal to x2 is the probability of x, or the probability of the random variable having values less than x2. Okay, and definitely this will be higher than f(x) of x1. Or you can also say it like this. Suppose if I have, this is x, which is the random variable values. If I take 2 points, maybe x1 and x2, and I define the CDF of the random variable at x2, which is probability of x less or equal to x2, and this I can write as, it means the probability of the all the values of the random variable having value equal to or less than x2, that is what will define the CDF at this point. Similarly, at x2, you have the probability of, for all the points, having value equal to or less than x1. I can decompose this range into 2 parts, maybe starting from minus infinity to x1 and then x1 to x2. So I can take it as the probability of x less than equal to x1 union x1 less than x less or equal to x2. Okay, so I am finding the probability of getting the random variable x from minus infinity up to x2. This is what is this function. Okay, and that in between I have defined the intermediate point x1. So I am first taking the probabilities from minus infinity to x1, including x1, and then for those points which are greater than x1 but less than or equal to x2, between this range. Okay, so definitely these two are disjoint events. Okay, and if the two events are disjoint, the probability of their union is equal to the sum of their probabilities. So this I can write as probability of x less or equal to x1, which will become fx of x1, plus probability of x1 less than x less or equal to x2. Okay, so definitely fx of x2 is fx of x1 plus this probability, and since this probability is always a non-negative number, so definitely this is always greater than this one. Okay, and from this you can also write that the probability of the random variable x between x1 and x2, okay, excluding x1 and including x2, can be taken as fx of x2 minus fx of x1. Okay, so if you the CDF can also be defined for discrete as well as the continuous random variable. If you take a suppose example in which we have to plot the CDF of a random variable, and the random variable x is defined as the number of heads appearing in a trial where the trial consists of 4 successive tosses of a coin. Okay, you have an experiment or a trial which consists of 4 successive tosses of a coin, and the random variable x is defined as the number of heads appearing in trial. So definitely when you toss a coin 4 times, you can have 16 possible combinations. Okay, like head, 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 tail, tail, and so on. Tail, 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 tail. So the random variable that you have defined, it is basically the number of heads appearing in each trial. So in the first trial, you have 4 heads. Definitely the values of the random variable can only be 4, either 0, 1, 2, 3, or 4, 5 values. Okay, so this is mapped to 4 because we have 4 heads in all the trials. In this case, you just have 2 heads, so it is mapped to 2. Similarly, you can map all the sample space outcomes on the real axis, and this is mapped to 0. Okay, accordingly, you can find the probabilities. The probability of 0 is the same as the probability of getting value of 4, and that will be simply 1 by 16. Likewise, you can find the probability of 1 is same as the probability of 3, which is 4 by 16, and that will be 1 by 4, because we will have 4 points. Okay, we have 4 sample space points in which are mapped to 1, and 4 points which are mapped to 3. Okay, likewise the probability of getting 2 heads is 6 by 16, which is 3 by 8. Okay, so you will have 6 outcomes in which 2 heads will appear. That is why the probability of getting 2 is 3 by 8. Now if you plot its PDF, definitely, so you have xi and probability of xi, 0, 1, 2, 3 and 4. The probability of getting x is equal to 0 is 1 by 16. Maybe I write here like this. Probability of getting 1 is 1 by 4, and also the probability of getting 4 is also 1 by 4. Okay, the probability of getting 1 and the probability of getting 0 and 4 is same, which is 1 by 16. The probability of getting 1 and 3 is same, which is 1 by 16, 1 by 4, and the probability of getting 2 is 3 by 8. This is the PDF. Okay, this is the probabilities. And then if you plot it CDF, x versus fx of x. So you have 0, 1, 2, 3, 4, 5, and so on. So probability of, now f of x is the probability of x less or equal to x. So when I take x is equal to 0, the probability of the random variable getting a value less than 0 is definitely 0. Okay. When x is any value between 0 and 1, the probability of this will be same as the probability of 0. So it will be 1 by 16. Okay, up to 1. When x becomes 1, then this 1, the probability at 1 will also be counted. Probability of x less or equal to x. It means the probability of 0 plus probability of 1. So it will become 1 by 16 plus 1 by 4. You get 5 by 6. Okay. Then as long as x is between 1 and 2, this remains same. When x becomes 2, the probability of CDF at x is equal to 2 is the sum of all the probabilities for x less than 2. It will get added. Next probability added. Okay. At 3, again you have addition. At 4, you have addition. And then it becomes 1. Definitely. Because after this, you have the sum of all the probabilities and it becomes 1. Okay. So this is what is the CDF. So CDF is basically a step function. Okay. Whereas in case of discrete random variables, your PDF is a discrete function and the CDF is a step function. Okay. Now for the continuous random variables, we should start from the CDF and we basically try to derive the PDF. Okay. So PDF, probability density function of continuous random variables. So we have already seen that equation that fx of x2 is equal to fx of x1 plus probability of x1 less or equal to x less or equal to x2. Okay, this already we have seen, just for this. Or you can say that the probability of x1, x lying between x1 and x2 is the CDF at x2 minus the CDF of the random variable at x1. Okay, so from this theory I can write f of x at x plus dx or x plus delta x as fx of x plus probability of x less or equal to x less or equal to x plus delta x. Okay, this is in tune with the SAM equation. The only thing is that x2 has been replaced with x plus delta x. Okay, and if you see the probability of getting, and of course your x1 is taken as x. Okay, x1 is taken as x and x2 is taken as x plus delta x, otherwise you have the SAM equation. Okay, so if delta x approaches to 0, and if you write this equation fx of x plus delta x in the form of Taylor series, if you find the Taylor series expansion of this, it can be approximately written as fx of x plus df of x divided by d of x into delta x, and you have higher terms, okay, double derivatives, but you just approximate it using the first order derivatives, because when delta approaches to 0, in the next you have delta x square, then delta x cube, so those higher terms can be ignored. Okay, so Taylor series basically expands a function in terms of its derivative at a particular point. Okay, so if delta x approaches to 0, then you can see that if you compare these two equations, this equation with this equation, so this derivative operator can be approximated by this value. Okay, derivative along with delta x. So I can say that as delta x approaches to 0, df of x over df x into delta x, it becomes probability of x less than x less or equal to x plus delta x. Okay, where the derivative of the CDF with respect to x, we call it as px of x, and this is what we define as the probability density function of the random variable. Okay, so if I define px of x as the PDF of the random variable, then px dx, px delta x, p of x multiplied with delta x, it denotes the probability of the random variable x having a value between x and x plus delta x. Okay, that is what is the meaning of the PDF now. So you have a CDF, see you have a CDF x and fx of x, which is a increasing function. So for any 2 points x1 and x2, if x2 is greater than x1, definitely f of x2 will be greater than fx of x1. And if you find the derivative of this function with respect to x, that is px of x, which we call as the PDF of the random variable. Okay, so you get its derivative, you get something like this, maybe suppose, and this p of x into d of x or delta x, px delta x, it now denotes the probability of finding the random variable x between x and x plus delta x. Okay, so if I take a small portion, if this is delta x and this is x, so px delta x basically represents the probability of getting the random variable x between x and x plus delta x, okay, over this interval. So absolute probability of the random variable at a particular x is 0. Okay, so what you can define is the probability of getting a value of the random variable, probability of the random variable within a certain range. That is why we have introduced first CDF, then we have derived the PDF from the CDF. Okay, so PDF, which is the derivative of the CDF, If you multiply this PDF with delta x, then that indicates the probability of getting the random variable between x and x plus delta x. Okay. Now, since your PDF is a derivative of CDF, I can write express fx of x in terms of integration of PDF px of x, or you can take some dummy variable, maybe px of u into du. Okay. So this is how you can express the CDF in terms of the PDF, because it is a derivative, so this will be the integral of this. And if you just put x is equal to infinity, and since this fx, the CDF at infinity is 1, accordingly you'll get minus infinity to infinity px of x dx as 1. So the area under the probability density function should be unity. Okay. In the discrete case, the sum of all the probabilities was 1. In the continuous case, the area under the PDF is going to be 1. Okay. Also, you can say that, so we have seen that if you, this is PDF px of x. So if you take a small interval x and x plus delta x, then px delta x defines the probability of getting a random variable between x and x plus delta x. Okay. So if you integrate, if you take suppose any 2 points x1 and x2, and you integrate the PDF between these 2 points, integration of between x1 to x2 px of x into dx, that will give you the probability of getting the random variable x between x1 and x2. Okay. And you can directly justify this. See, if I say the probability of getting x random variable between x and x2, that is nothing but this should be less than, okay, not equal to, it should be f of fx of x2 minus fx of x1. This is what we have already seen, and this I can take integral of minus infinity to x2 px of x into dx minus integral of minus infinity to x1 px of x into dx. So this is, I am expressing the CDF in terms of PDF as the integral of PDF. And these two integrations, if you find the difference, minus infinity to x2, you will get this area, minus infinity up to x2. You will get the entire area starting from the minus infinity up to x2. And then minus infinity to x1, you will get the area up to this point. Okay. And if you find the difference, definitely you'll get the area under the curve between x1 and x2. Okay. So that is why we had written. So if you integrate the PDF between x1 and x2, that will give you the probability of observing x in the interval x1 and x2. Okay.